Some chemical processes can happen in both the forward and reverse directions. Consider the example of phase changes, and we'll look at the specific example of water. Water can be in the solid state, that is, it can be ice, and you can cause that solid water to melt and turn into liquid water. So you can have a process that works in one direction. You can also take that liquid water and cool it down and convert it back into H2O solid, back into ice. And for a reversible process like this, where there are two different reactions that you can write that just represent going in one direction and then reversing that process, we can write a simplified version using an equilibrium arrow. An equilibrium arrow is just made up of two half arrows pointing in opposite directions, and it implies that the process can go in both directions. And we can also have this happen with chemical reactions. Consider the example of nitrogen monoxide reacting with bromine. Nitrogen monoxide and bromine can react to make the NOBr molecule, but NOBr can also decompose to make nitrogen monoxide and bromine gas. When the rate of the forward reaction or process is the same as the rate of the reverse reaction or process, you have what is known as a state of chemical equilibrium. So at equilibrium, the forward reaction is making NOBr, and the reverse reaction is making NO and Br2 at exactly the same rates, so that the concentrations of each component is going to stay constant. The concentration of NOBr is constant, and the concentrations of NO and Br2 also remain constant. And we can represent this graphically as well. Imagine that we start a reaction with a concentration of NO of 0.2 and a concentration of bromine gas of 0.1 and a concentration of NOBr of 0. That is, we mix some nitrogen monoxide with some bromine gas and we're hoping to make NOBr. So initially what will happen is the concentrations of nitrogen monoxide and bromine gas will start to decrease. And the concentration of NOBr will increase because you're producing it. And as you produce NOBr, some of the NOBr molecules can decompose and reform the nitrogen monoxide and the bromine gas, which means that the concentration of NOBr will probably still increase a little bit, but the rate at which it does so will begin to slow. And eventually the concentrations will change and stop at the point where the rate of decomposition of NOBr is exactly equal to the rate of reaction of NO and Br2. And at that point, the concentrations will stop changing for all components. And this same kind of thing can happen if you start with wildly different amounts of material. We can draw the same graph, but with different concentrations of starting materials. So we'll start out with a larger amount of NOBr. And we'll start with 0 concentration of NO and Br2. And what will happen is, initially, you have NOBr in the system, and it will start to decompose and form NO and Br2. And as that happens, the NO and Br2 concentrations will increase. And at equilibrium, the relative amounts of each material are always going to be the same, no matter if you start with all reactants or all products or a mixture of reactants and products. The relative amounts of each one will be the same. The absolute amounts can be totally different, but the relative amounts of product and reactant will always be the same at equilibrium conditions. And because this relative amount of product and reactant is constant, it implies that there's actually a constant numerical value that's proportional to the amounts of reactants and products. And that value is given the symbol K. And this K value is going to be specific to each individual reaction. That is, every different reaction will have a different K value.